Hi, today we are looking at the limits of trigonometric functions. So first we'll review some graphs and then we'll look at our limits. So first graph you should recognize from pre-calculus 12. So this is our graph of y equals tan x. So if you recall from pre-calculus 12, you have vertical asymptotes, a negative pi over 2, and then they repeat essentially every pi. Now, if we were to say look at our limit as we approach pi over 2 of this, we can see that our our limit as x approaches pi over 2, if we're approaching it from, say, the negative side, so from this side, we're going towards positive infinity. Where if we look at that same limit as we approach pi over 2 from the positive side, we can see that we're going to negative infinity. So you can see our left-hand limit and right-hand limit do not match with tan x. Similarly, we'll have other trigonometric functions where these limits do not equal each other. So if we look at our reciprocal of tan x, which is cotangent x, we have something that looks like this. So notice that once again, we have asymptotes that are exactly pi apart. And in this case, they are at multiples of pi. If we look at our limit as, let's say, we approach 0, so our limit as x approaches 0 from, say, the negative side for cotangent x, we go towards negative infinity. Where if we have limit as we approach from 0 from the positive side of cotangent x, we can see that we're going to positive infinity. So once again, these do not match. So we know we do not have a limit. Next, we've got secant x. So this is our reciprocal of our cos function. So once again, you'll see that we once again have vertical asymptotes that are pi apart. And what we can see is as we approach either asymptote, on one side it's going to positive infinity, where on the other side it goes to negative infinity. Same with our reciprocal of cosine y equals cosecant x. Once again, vertical asymptotes, and our limits on each side of those asymptotes go to opposite signs of infinity. Now, for the most part, we won't deal with these ones that are going to opposite signs. Instead, we're going to be looking at ones that are involved in functions where we have a limit of indeterminate form 0 over 0 for trig functions. So I have three limits listed here, and on the next few pages, we will prove each of these. So we've got our limit as x goes to 0 of sine x over x equals 1. So we know from our graph of sine that as x approaches 0, sine is going to equal 0, and then that's divided by 0, so that'd be our 0 over 0. And that's the case for each one of for tan as well. So we know tan of 0 is 0, and we're going to 0. Now, with this one, it's slightly different because we know cos of 0 is 1, so this would be 1 minus 1, giving us 0 over 0. So limits of the sine x over x equals 1, tan x over x equals 1, and our limit as x goes to 0 of 1 minus cos x over x gives us 0. So like I mentioned, we will go over the proofs of these on the next few slides. So first proof, we're going to prove our limit of sine theta over theta, or I should have sine x over x equals 1 as x goes to 0. Actually, let's go back, and because these were already thetas, let's say as theta goes to 0 instead of as x goes to 0. So we're going to prove our limit sine theta over theta as theta goes to 0 is equal to 1. So to prove this, I will draw out a diagram. We're going to start by drawing out a circle. Now the center of that circle we'll mark as O for our origin. We'll draw a couple lines off of that. So one that's just simply our radius. And then we'll draw a line that's perpendicular to our radius. It goes to some point outside our circle. And then we'll draw from our origin to that line. Now we'll label it. So we know this is R. We know essentially from here to here would be R. Here's our angle theta. We're going to call this point A. Like I mentioned, this is 90 degrees, so I'm going to mark that as 90 degrees. I'll call this T, and I'll call this point here where these two meet as B. Now, I'll draw in one more line. I'll just do it in a different color so that we can see it a bit better. So we'll draw a line from A to B. And then we're going to be using some formulas that we looked at earlier on in the course. And we're essentially going to be looking at three main areas. So what we're going to look at is our area of sector OAB. So in other words, the area created by this triangle. We're also going to later on look at the area of triangle AOB. So first would be this sector, second would be this triangle, and third would be this larger triangle, OAT. Now to get our area of this sector, we know that total area of a circle is pi r squared. So the area of this sector here is going to be equal to the percentage of our total circle that is represented by that. So we can say it's our area of the total circle times essentially the percent way around our circle, or ratio of the way around our circle, which would be theta over 2 pi. This can simplify a little bit. So our area is going to be our angle times r squared over 2. Or another way to write this is 1/2 theta r squared. Now, we're going to next look at area of triangle AOB. So that would be this triangle here, this non-90-degree triangle. Now we know that that would be equal to 1/2 AB sine of C. So in this case, that'd be 1/2 times R times R sine of theta. So that gives us our area is 1/2 R squared sine theta. And then we're going to look at this larger triangle, the 90-degree triangle. So area of triangle AOT, which would be our area is 1/2 our base times our height. So we've got 1/2 times our base, which is R, times our height, which if we're solving for that height, that's utilizing tan, because we technically know this, and this would be our opposite, this is our adjacent, so that's tan. So to actually solve for this height, that would be r tan theta. So the area of this large 90-degree triangle is 1/2 r squared tan theta. Now, if we look at the three shapes that we have that we calculate our area for, we can see that probably this arc sector, or this sector here, or sorry, the area of this triangle here, should be the smallest area, because we can see the area of this sector includes not only that triangle, but this little bit here. So therefore, we can say the area of this triangle, so that's area of triangle AOB, we know must be less than the area of this sector, which is slightly bigger. Which we know must be smaller than the area of this 90-degree triangle that contains both other shapes. Now we've come up with equations for each of these. So our area of triangle AOB is 1/2 r squared sine theta, which we know is less than our area of our sector, which is 1/2. Let's just reorder this, so r squared theta, which we know is less than the area of triangle AOT, which is 1/2 r squared tan theta. Now, what we'll do next is something that you probably noticed, which is everything here has 1/2 r squared. So we can divide 1/2 r squared out of all three terms because it's essentially acting as a constant in all three. When we do that, that gives us sine theta is less than theta, which is less than tan theta. Now we're going to rewrite this in terms of sine and cos. So that gives us sine theta is less than theta, which is less than sine theta over cos theta. So our next step in this proof isn't quite as intuitive as this step, and it is to divide everything by sine theta. Now, if I divide sine theta by sine theta, that gives me 1. If I divide theta by sine theta, that gives us theta over sine theta. And if I divide sine over cos by sine, that's just going to give us 1 over cos theta. Now, because our original proof is sine over theta, but we've got theta over sine, what we're going to do next is take the reciprocal of everything. Now, because we're taking the reciprocal of everything, it also changes the direction of our inequalities. So it'd give us 1 is greater than sine theta over theta, which is greater than cos theta. Now, as theta goes to 0, cos theta, when theta is equal to 0, equals 1. So we essentially have 1 is greater than sine theta over theta, which is greater than 1. So essentially that tells us that sine theta equals 1. So therefore, we can say our limit as theta goes to 0 of sine theta over theta equals 1. Okay, so that was the first of the three proofs. Next, we're going to prove the tan one. Now, this one isn't as long of a proof. So we're going to prove our limit as x goes to 0 of tan theta over theta equals 1. So I'll just start by rewriting this. So I've got our limit as x goes to 0 of tan theta over theta equals 1. We can rewrite this using sine and cos. This is the same as our limit as theta goes to 0 of sine theta over cos theta divided by theta. Actually, for now, we won't include the equals 1 because we're just looking for proof. Now, if we have our limit of sine theta divided by cos theta all divided by theta, that can be written as our limit as theta goes to 0 of sine theta over theta cos theta. Now we're going to utilize a limit that we just learned or proved on the previous page. So as x goes to 0, that's our limit of sine theta over theta times 1 over cos theta. Okay, so we just proved that this one is equal to 1, so that'd be our limit of 1 times. As theta goes to 0, that would be cos of 0, which we know is 1, so times 1 over 1. Therefore, we know our limit as theta goes to 0 of tan theta over theta must equal 1 times 1 over 1, so that just gives us 1. Okay, next, we want to prove our limit that 1 minus cos theta over theta equals 0. Okay, so I'll start by rewriting this. We've got our limit as theta goes to 0 of 1 minus cos theta over theta. Now, what I would do with this one is multiply the numerator and denominator by 1 plus cos theta, or in other words, the conjugate of our numerator, because that's going to give us our limit as theta goes to 0 of 1 minus cos squared theta over theta times 1 plus cos theta. Now, you may recognize this as something that can be simplified using a Pythagorean identity. So this becomes our limit as theta goes to 0 of sine squared theta over theta times 1 plus cos theta. Now we're going to break this apart into two separate things that are multiplying by each other, because essentially we know once again that sine theta over theta as theta goes to 0 is 1. So we want to split it up. So we'll factor that out. So if I have sine theta over theta times what's remaining would be sine theta over 1 plus cos theta. Now we know that sine theta over theta as theta goes to 0 is 1. And then we know that if we substitute 0 in for these, theta sine of 0 is 0 over 1 plus cos of theta. Cos of 0 is 1, so 1 plus 1 gives us 2. So we've got 1 plus, or sorry, 1 times 0 over 2, so that's just going to be 0. So therefore, we can say that our limit as theta went to 0 of 1 minus cos theta over theta is equal to 0. Now we're going to utilize some of these to come up with more rules. So we've got our limit as x goes to z of sine y over y equals 1. And our limit as x goes to z of tan y over y equals 1, where y must approach 0 as x approaches z. So in other words, y is some sort of function that as x goes to z becomes equal to 0. So as long as we have the same function inside our, say, sine function and our denominator, or in our tan function and our denominator, and that function is going to 0 as x goes to z, our limits equal 1. Okay, so for example, evaluate the following limits. So our first one we're going to look at is our limit as x goes to 0 of sine x over 2x. So this looks very similar to what we've already dealt with. I'm just going to rewrite it over here. So we've got our limit as x goes to 0 of sine x over 2x. So what we can do is break this up. So this is our limit as x goes to 0 of 1 over 2 times sine x over x. Now we can move the 1/2 in front of our limit because essentially it's a constant. It's not affected by our x. So this would give us 1/2 our limit as x goes to 0 of sine x over x. Now we know our limit of this is 1, so that would be 1/2 times 1, which gives us 1/2. This next one, we've got our limit as x goes to 0 of sine 2x over x. Now this one's a bit more challenging than the past one because we can't really get something out of this sine function. Instead, we're going to utilize one of those last rules. So we know that if we have sine of 2x over 2x, it's going to equal 1. So we have to think about how we can make this 2x down here. So I'll just rewrite our function here, and then we will go about doing exactly that. Okay, so if we want a 2 down here, I'm going to have to multiply this by 2. But in order to not change the function, I have to multiply numerator and denominator by 2. So that's going to give us our limit as x goes to 0 of 2 sine of 2x over 2x. Now we can simplify this a bit because that's the same as our limit as x goes to 0 of 2 times sine of 2x over 2x. We can move this constant to front, so that's 2 times the limit as x goes to 0 of sine of 2x over 2x. Now we know from our rules that this equals 1, so this would be 2 times 1, so that gives us a value of 2. Next one, slightly more complex. We've got our limit as x goes to 0 of sine 2x over x squared plus 5x. I'll just once again rewrite that. So we've got our limit as x goes to 0 of sine 2x over x squared plus 5x. So first thing I would do with this one is factor this denominator. So we've got our limit as x goes to 0 of sine 2x over, we can factor an x out, so that's x times x plus 5. So in order for us to use our rule, we need a 2 in front of here, so I will then multiply both of these by 2. That gives us our limit as x goes to 0 of 2 sine of 2x over 2x times x plus 5. We can then break this up, so this is the same as our limit as x goes to 0 of sine 2x over 2x times, we have the 2 in front, and we have the x plus 5 down here. So we know that this will equal 1, and then if x is going to 0, that would be 2 over 0 plus 5, so times 2/5. So this equals 2/5. Okay, next example, we've got our limit as x goes to 0 of sine of 7x over sine of 4x. So what we're going to want to do is create fractions within this fraction to help us solve this. So we've got our limit as x goes to 0 of sine 7x over sine of 4x. So we want to get this so we can have sine of 7x over 7x, and we want to get this to sine of 4x over 4x. So therefore, this one I would multiply by 7x over 7x, and our denominator we're going to multiply by 4x over 4x. So that gives our limit as x goes to 0 as 7x times sine of 7x over 7x over 4x times sine of 4x over 4x. Now we'll do part of a limit now. So we know this as x goes to 0 is going to equal 1, and this will too. So this is the same as saying 7x times 1 over 4x times 1. So we're looking at our limit as x goes to 0 of 7x divided by 4x. But what you'll notice is both these terms have an x, so we can cancel those out. So that just gives us 7 over 4. Okay, next one, bit more complex. So we've got our limit as x goes to 0 of sine of tan x over 2x. So because inside of a sine function we have tan x, we need tan x in this denominator. So I'll rewrite this. So we've got our limit as x goes to 0 of sine of tan x over 2x. Like I mentioned, we need to get tan x in our denominator so that we have the same thing inside our sine function as we have in our denominator. So that means I'm going to have to multiply the numerator and denominator by tan x. So that would be tan x times sine of tan x over 2 tan x sine x, or sorry, 2 tan x. So we'll split this apart a bit. So we've got our limit as x goes to 0 of sine x, or sorry, sine of tan x over tan x times that leaves tan x over 2x. Now, we know that from our rule a few pages ago, but if we have the same function inside sine as we have in our denominator, that's just going to equal 1. So this will just be our limit as x goes to 0 of 1 times, I'm going to split this up, that's the same as 1/2 times tan x over x. Now we know tan x over x as x goes to 0 is 1, so we have 1 times 1/2 times 1, so that just equals 1/2.